The reactions of the alkyne or reaction of the acetanilide ion as the acetylide ion as a nucleophile. It can be added to alkyl halide. We looked at that already. So if you have acetylide ion, that is the CC triple bond with the negative charge after you remove the hydrogen, basically. So if we take like a step back, we have the acetylene. We are going to add sodium amide as a strong base, is going to remove the hydrogen from the acetylene. Then we have acetylide ion. Acetylide ion, it can react with alkyl halide plus, let's say if you have ethylene bromide, in this reaction, you would get the nucleophile. So we have the nucleophile, we have the leaving group. So a nucleophilic attack, the leaving group would leave, and you increase the carbon chain. So your final product is going to have 4 carbon instead of 2 carbon that you have for acetylene. Other reaction of the acetylide ion. So when we talk about acetylide ion, we are talking about the acetylene that has lost hydrogen, or terminal alkyne that has lost the hydrogen. Now we have a negative charge on the carbon-carbon triple bond. It can act as a nucleophile. A nucleophile can attack carbonyl group. With the carbonyl group, since if there is no leaving group, then the pi bond will break over the oxygen. You protonate the oxygen, you have OH. So basically, you are going to prepare alcohol. So acetylide ion acting as a nucleophile, when it attacks the carbonyl group, or any nucleophile attacks the carbonyl group, you have to first look at the groups that are attached to this carbon. With any of them are, it's the leaving group, then the leaving group would leave. If none is leaving group, then the pi bond will break over the oxygen. You protonate that, you get the alcohol functional group. So acetylenic alcohol, that means that you do have a triple bond and alcohol on the same molecule. Okay. Next type of reactions that we have, or specific examples of it. If you have this ion, the acetylide ion, adding to aldehyde, just like Grignard. Remember from Grignard reaction, Grignard plus formaldehyde would give you primary alcohol. Grignard plus aldehyde would give you secondary alcohol. In this case, instead of the Grignard, you have the acetylide ion, and acetylide ion plus the aldehyde would yield secondary alcohol. You have the secondary alcohol. Acetylide ion plus ketone would give you tertiary alcohol. So the pattern is going to be the same as Grignard reagent. In Grignard reagent, you have the negative, or RMGX. The carbon attached to Mg is going to carry the negative charge. In this case, you have the acetylide ion, and the carbon from the triple bond is going to carry the negative charge. So you have basically, it's a nucleophilic attack on the carbonyl group. And if you have the formaldehyde, primary alcohol, the aldehyde in general is going to give you secondary alcohol, but how many carbon you bring from the alcohol that or you add to this nucleophile, it depends on which aldehyde you would choose. If it's a acetaldehyde, you would add 2 carbon, but if it is propanol, you would add like 3 carbon. Regardless of the number of the carbon on the aldehyde, you end up with a secondary alcohol. When you add to ketone, you get tertiary alcohol. So in this example, you're trying to make this alcohol. When you're preparing this alcohol, is first of all, you have to find out this is a secondary alcohol. So because this is a secondary carbon, secondary alcohol. If it's a secondary alcohol, then what should be your carbonyl group? Carbonyl group. Your carbonyl group must have been aldehyde, because your product is a secondary alcohol. So the part that is coming from terminal alkyne is starting with the carbon-carbon triple bond and everything that is included or attached to carbon-carbon triple bond, because your carbon-carbon triple bond, the terminal alkyne, the last carbon or the first carbon is going to be negatively charged, or this part is coming from the nucleophile, and the other side of the molecule is coming from carbonyl group. So the fact that this is a secondary alcohol, we know our carbonyl must be aldehyde carbonyl. And then you start with the alkyne, a terminal alkyne with 1, 2, 3, 4 carbon. Then you start with terminal alkyne, 4 carbon. You add sodium amide. If there is no restriction, you can start with this. Then this would give you a negative charge on the last carbon. This is going to be the nucleophile. Then you want this structure, but in form of the aldehyde. So if you take this blue part or the blue circle now back to aldehyde, is going to be CO double bond on this carbon. So you add that cyclopentyl carbaldehyde, cyclopentane carbaldehyde, you add that. Then nucleophile is going to attack this, pi bond breaks over the oxygen. This is the case that there is no restriction, right? In this case, how would you synthesize the following compound, beginning with acetylene? So if you want to start with acetylene, that would be your restriction. How would you modify this? Acetylene, you have to first add the ethyl group to acetylene. So you start with the acetylene, you remove the hydrogen, and then you add ethyl bromide. I had this example before. So you have the acetylene, remove the hydrogen, you get the negative charge on the acetylide ion. Then you add ethyl bromide because you want 2 additional carbon. So you have to see how many carbon is missing from what you need compared to acetylene. 2 carbon is missing, that's why you're using ethyl bromide. If 3 carbon were missing, then you would use propyl bromide. So basically you have to go like a retro synthesis and find out you need the 4 carbon. 2 carbon is coming from acetylene, the other 2 carbon must come from alkyl halide. Then on the next step, your aldehyde, which is your carbaldehyde or cyclopentane carbaldehyde, it will be added, followed by hydrolysis, because the alkoxide that is formed here, the negative charge needs to be protonated. That's why you have to follow it by hydrolysis or bring a protonate this alkoxide. Questions? I don't see new questions, so I will continue for the next reaction. How would you prepare alkyne? To prepare alkyne, the first step was to start with the acetylene and increase the carbon chain. So in that case, you must have like a terminal alkyne. And then another method to prepare alkyne is elimination reaction or dehydrohalogenation reaction from alkyl halide. It must be like dihalide or vicinal dihalide or geminal dihalide. Either one of them can be used. So if you have a vicinal dihalide, just like elimination reaction, you need to remove X and remove H from adjacent carbon. And when you do that, is going to give you a double bond. So you start from alkane minus HX, you get the alkene. Now, since you have like a vicinal dihalide, there is additional halide that you can remove now. On the next step, you have to remove it with the hydrogen from adjacent carbon to generate the second pi bond. The base that you're using here in this step must be a strong base because removing hydrogen from vinylic carbon is not easy. So you do need a stronger base, okay? A stronger base for the second step. The other reactant you can start is a geminal dihalide. In a geminal dihalide, it would be the same. Basically, you're removing X from one carbon and hydrogen from another carbon. That would give you alkene. Then you remove X and hydrogen from two adjacent carbons. Then that would give you alkyne. So it's two-step. First step, removing the first hydrogen that you are bringing a base is not going to be too much of a challenge, but the second step is very hard to remove hydrogen from vinylic carbon, and as a result, you need a strong base, stronger base.
So it's harder the second time around.
Yes, it's harder to the hydrogen second time. Yes. For elimination reaction, heat favors the elimination reaction. The amount of the heat that you are using here, it's about 200 degrees Celsius or 100 degrees Celsius, and then you are using sodium amide. For different condition, you're going to get internal alkyne versus when you have two possible, okay? When there are two possible products, if you set the condition of the reaction with potassium hydroxide and 200 degree, you get internal alkyne. But if you set it at 150 with sodium amide, you would get terminal alkyne. That would be the case that you have, let's say you have a geminal, let's say you have a geminal dihalide, you have hydrogens, and you have hydrogens. Hydrogens on the left, hydrogens on the right. Basically, what this statement says that if you set the reaction condition 200 degrees Celsius, use KOH, okay, you would remove the red hydrogens, but if you set the reaction conditions using sodium amide and 150 degrees Celsius, you would remove the blue hydrogens. And removing the blue hydrogens from the beginning of the chain is going to give you terminal alkyne, and removing the red hydrogens from the inner carbon, it would give you internal alkyne. So with the red ones, red conditions, you would get triple bond between carbon 2 and 3. With the blue condition, you would get terminal alkyne like this. So it depends on the condition that you use for the reaction mixture.
So you could get both conditions in one molecule, pretty much?
No, you have to choose which one you want to do. You want to get an internal alkyne, or you want your product to be terminal alkyne. So basically, if I put it this way, is better. So two separate arrows, not the same arrow. Okay. So if your condition is 200 degree and KOH, you get internal alkyne. If the condition is 150 with sodium amide, you would get terminal alkyne. Okay. Reactions of alkyne or addition reactions of alkyne, when you have a carbon-carbon triple bond, you have one sigma bond and one sigma bond and 2 pi bonds. So you can break one of these pi bonds, you add 2 sigma bond, or you can break both pi bonds and you add 4 sigma bond. So the reaction often is exothermic because you're breaking pi bond, but you're making sigma bond. Sigma bond is formed. So the reaction is going to be exothermic. Each pi bond you break, you add 2 sigma bonds. If you break 2 pi bonds, you add 4 sigma bonds. Okay. So you could add 1 molecule or you could add 2 molecules. Okay. Now, if you want to add 1 molecule or 2, you have to again set the reaction condition. Pick a proper reaction condition. If you're adding hydrogen with any of these 3 catalysts, hydrogen with palladium or platinum or nickel, the saturation is going to be complete. So you are going to add 2 molecules of hydrogen and change the alkyne to alkane. Now, if you want to add only 1 molecule of H2 and stop it in the alkene, okay, in the alkene state, you want to stop it. Basically, you're breaking one of the pi bonds. The catalyst that you are using, it must be poison catalyst. So the reaction condition must be mild condition. So in order to poison the catalyst, you are going to, instead of using palladium, like pure palladium, you are going to mix that with barium sulfate. So basically, you are poisoning the catalyst, or you are poisoning the reagents that you are using for hydrogenation. And if you mix, if you see that if you're not poisoning, all full saturation will happen. But if you poison it, you are going to get only one of the pi bonds broken, 2 hydrogen is added, and you would get alkene. Specifically, you are going to get cis alkene. So from now on, from alkyne going to cis alkene, you must know that this is the set of the reagent you are using. The name of this set of reagent is called Lindlar catalyst. So other than hydrogen, everything else is called Lindlar catalyst. And then with the hydrogen is going to be Lindlar reagent set. Hydrogen, palladium mixed with the barium sulfate, and then quinoline and methanol. So the mixture of all these reagents, it's known as the Lindlar catalyst. The difference is you are going to get a cis product. Why cis product? You remember from hydrogenation of the alkene, I said because addition happens at the surface of a solid catalyst. So basically, hydrogens are already on the surface of the catalyst. Alkyne comes in, and then this kind of forms a bridge, and hydrogen adds at the surface of the solid catalyst to each of these carbon. So addition happens as a syn addition from the same site, and since addition of the hydrogens happens from the same site, then the R groups are going to be on the opposite side, and the product is going to be cis product, because you have a solid catalyst, and this is partially poisoned palladium. How do you poison it? You would use the Lindlar catalyst, okay, with the Lindlar catalyst. Now, these are some examples. The point of this Lindlar catalyst is a cis product, okay? So the 2 hydrogens are added from the same side. The alkyl group that are attached to carbon-carbon triple bond at the reactant side would be on the same side of the carbon-carbon double bond on the product side, because one of the pi bond has been saturated. So it adds from the same site. It's known as the Lindlar catalyst. Now, how can we, if we can make cis product, how can we make trans product? To make the trans product, you have to change your reagent. And in order to make trans product, you're going to use the metal with ammonia. So what happens in this case, in order to saturate, you need electron and you need hydrogen, okay? You need electron and you need hydrogen because you want to add 2 hydrogens. So sodium provides electrons. Sodium provides electrons. Ammonia would provide the hydrogen. Just kind of make it easier for you to remember that you need sodium and you need ammonia. So you need sodium and ammonia. So you need electron. So electron is going to be added first because sodium is more reactive than the ammonia. Sodium is going to lose an electron to the alkyne. And then if you bring 1 electron here to one of the, if you bring 1 electron to this carbon-carbon triple bond, one of the carbons, the carbon already has 8 electrons. So the loose bond or the weakest bond is going to break, and that's pair of electron that is going to break the pi bond and it would go to the other carbon. So if I show you on the next slide, it's a better picture than what I draw here. Okay, it's the nicer picture. Okay, electron is going to be added to one of these carbons. It doesn't matter which one, to one of these carbons. Like electron is added from the top. The other pair of electron is going to go away from these electrons. So if you have 1 electron up here, the pair of electron is not going to come here because it's too close to one another. And these pair of electrons are going to repel each other. Remember, like charges, they repel, opposite charges, they attract. So this pair of electron is not going to stay here. The pair of electron would be on the opposite side compared to this electron that we have here. So they are in the opposite side. Now, the pair of electron with the negative charge that you have here, this is acting as like a strong nucleophile or strong base. It can abstract a hydrogen from ammonia. So it will take a hydrogen from the ammonia. So now we have a vinyl radical. It's very unstable, it's not stable. So it's going to require an additional electron. And who is going to give that electron is another sodium. Sodium is going to lose 1 more electron to this free radical. So it's going to get changed to the anion again. So free radical would get electron from sodium and changes to anion. So now that you have anion is acting as a nucleophile or strong base, okay, is a strong conjugate base, is going to abstract a hydrogen from ammonia. So if you look at the steps to remember these steps easily, you would say you have sodium and you have ammonia. Sodium will provide electron, and then ammonia will provide hydrogen. So sodium gives electron, ammonia gives hydrogen. So that's step 1, step 2. And then step 3, sodium would give electron, and 4, ammonia would give hydrogen. So sodium provides electron and ammonia provides the hydrogen. And you add 2 electron and you add 2 hydrogen, basically 2 H pluses and 2 electrons. The part that makes sure the product is trans is the initial or the first step. Remember I said if you have the electron that's coming from sodium, it would be on the up top. The pair of electron would go to the opposite direction at the bottom. This is backbone of the molecule already translates to a trans. So everything else is going to follow this pattern. You already have a backbone of a trans molecule. the R groups are pushed to opposite direction because electrons are pushed to opposite direction. You're adding one hydrogen and then add electron and then hydrogen. It doesn't matter. R groups are pushed to opposite direction already. So we get a trans product. So you can do hydrogenation of alkyne. If you add 2 moles of H2, the product would be alkane. If you add 1 mole of H2, you can get alkene, either cis or trans. If the catalyst that you are using is a Lindlar catalyst, you would get cis product. If the catalyst that you are using is the sodium, metal, and ammonia, you would get trans product. Now, next reaction. Do you have any question about hydrogenation before I talk about next reaction? If there is no questions, next reaction is addition of halogens. Addition of halogens, it can be, there's no, you get mixture of the product. You can get cis or trans product. If you add CO2 or you add the Br2, you could get, but in general, trans is more stable than cis. You also had a question like that in the previous exam for alkene. If it's trans, is more stable than the cis alkene. And that could be the reason for 72% versus 28% because it's more stable. If you add 2 molecules, then you get both pi bonds break and you get tetrahalide. So your dihalide is going to change to tetrahalide because really the bromine, addition of bromine to pi bond is so fast that this reaction is called test for unsaturation. So when you add bromine, it would react right away with the pi bond. Since you still have pi bond left, then it would be hard to stop the reaction here and it can continue and break the pi bond again, and you get tetrahalide as a product because you have alkyne. 2 pi bond breaks and 4 bromine is going to add. What happens if you add HX? Now, when you're adding HX, then you have to talk about Markovnikov or anti-Markovnikov. Would it be Markovnikov addition or anti-Markovnikov addition? It depends on it, especially for the terminal alkyne. It depends on the catalyst that you are using. So in this case, when H is added to the first carbon, it's going to be carbon with the greater number of hydrogen. So it is a Markovnikov product. This is it kind of applies for the terminal alkyne. If the alkyne is an internal alkyne, you could get mixture of the product. You can get the hydrogen added to either one of them, and then bromine add to the other one. So addition of the HX to terminal alkyne, it depends on the catalyst that you are using. So in addition of the HX, H is added first. Remember, you're not bringing other catalysts. So HX is acid. So basically, is like 2 in 1. Your HX, it provides the electrophile and the nucleophile, and H, it can act as a catalyst. So H will come in first. When H comes in, the other carbon will take the plus charge. So it's better for the hydrogen to go to terminal carbon. So the internal carbon would take the plus charge. Obviously, it would be more stability of the carbon. And the addition is going to be Markovnikov orientation. For anti-Markovnikov orientation, you have to change the mechanism of the reaction. And instead of adding HBr directly, you have to bring in the peroxide, alkyl peroxide. Remember, anywhere we have these peroxides, the addition is going to be anti-Markovnikov addition. So you would use the peroxide. When you use peroxide, the mechanism of the reaction is changing from carbocation to free radical in addition reactions, and still it follows the more stable free radical or more stable intermediate. Okay. Next reaction. So we added hydrogen, we can get cis or trans. We added halide, it's very hard to stop, it goes all the way. That's like when you're adding Br2 or Cl2. We add HX. HX can be added Markovnikov or can be added anti-Markovnikov. For anti-Markovnikov, you need the HO, OR or alkyl peroxide. For next reaction, which is addition of water to terminal alkyne, it can be Markovnikov or anti-Markovnikov as well. So if you add the H with the Markovnikov addition, and how do we know Markovnikov addition? You look at this reaction, the reagent that is used for the Markovnikov. Mercury sulfate, mercury 2 sulfate. Remember mercury 2 acetate, oxymercuration, demercuration. You had mercury with Markovnikov. So mercury would always go with Markovnikov. When you have peroxide, it would go with anti-Markovnikov. So that kind of makes it easier for you to remember. So when you have the mercury sulfate as a catalyst, this addition is going to be Markovnikov addition. What is the Markovnikov addition? H will add to the carbon with more number of hydrogens, and OH will add to the other carbon. So if you look at this carbon now, or this carbon now, okay, this carbon, it carries OH, which is all, we knew that, and then it also carries the CC double bond, which is in. So if you combine these two, because both of them are in the same carbon, because both functional groups are in the same carbon, you can combine these two, and is known as enol. So we have enol here, okay? Enol. Enol is not very stable. Enol can rearrange to ketone or aldehyde. If the OH is on the first carbon, it would rearrange to aldehyde. If the OH is on the second carbon, it would rearrange to methyl ketone. So you have a methyl, CH3, and this is the ketone. So basically, when you say ketone is like RCOR, and if you say methyl ketone, that means one of these R groups definitely is methyl, regardless of the other one, whatever it is. So this is a methyl ketone. So for terminal alkyne, when you add water with Markovnikov reagent or mercury 2 sulfate, the addition is going to be Markovnikov, means OH adds to the second carbon. So you have your enol is going to rearrange to ketone or methyl ketone. That rearrangement is called tautomerization. The spelling of the tautomerization is right here, that rearrangement. Basically, it's like formation of isomers, but it is like a very specific type of isomers, the tautomers. The hydrogen from the OH is going to move to adjacent carbon. So if the hydrogen from the OH group, so if we have the OH group here, the hydrogen from the OH group moves to this carbon, okay, moves to the other. So we are here, okay. It adds to this hydrogen. The oxygen would change to double bond oxygen. So that's tautomerization. They're in isomers, only pi bond would move around and pair of unshared electrons. But in tautomerization, hydrogen also is going to move around. Just make sure you know the rearranged form of these enol to ketone, how it's going to look like. So if you have this enol here, you have this enol here, and when it changes to ketone, the carbon that has the OH is going to have the CO double bond. The other carbon, instead of 2 hydrogen, now is going to have 3 hydrogen. So you have methyl ketone. This is a methyl ketone because one of the R group is methyl group. But the addition is addition of water. Hydrogen is added to the least substituted carbon, and OH is added to the other carbon or the more substituted carbon. Hydrogen is added to carbon 1 and OH is added to carbon 2. So for the these two are Keto-Enol Tautomerisation. In tautomerization, you have your hydrogen moving from the OH to adjacent carbon, and the pi bond would carry over and you get the CO double bond. So it's known as the enol keto tautomerization. Okay. In the reaction mixture that you have, like an acidic mixture that you have here, keto is more stable than the enol. And the reason for that is by experiment and by the sign of the size of the arrow sign in the that separates the two isomers from each other. These are specific isomers that is known as tautomers because it's only by rearrangement of one of the hydrogens. The arrow sign to the right, which is formation of a ketone, is longer. That means product is more favored than the reactant if we take this as a chemical reaction or as a process. Now, the mechanism of this reaction, if you want to go to mechanism, is acid catalyzed. It could be acid catalyzed or it could be like a base catalyzed reaction. So what's going to happen if it's acid catalyzed reaction, H plus is going to come in. You have carbon-carbon double bond. The H plus is going to add to the carbon that has more hydrogens. The other carbon will take the plus charge, and the plus charge on the other carbon is not very, stable. So it can be rearranged or it can be shared between the carbon and oxygen. Pair of electrons from the oxygen can come in to form the double bond to take over that plus charge, because plus charge is not welcome here either, because oxygen doesn't like plus charge. Then when you remove this hydrogen, that's why we call it acid catalyzed, because H plus comes in, H plus is leaving. So the net result would be CO double bond is forming, and the CC double bond is going to be saturated. So you add a hydrogen to the first carbon, and the COH would change to CO double bond. I know we have a lot of reactions, a lot of reagents for you to memorize. So please start working on end of the chapter problems, start working on the chapter assignment, and do not wait until the 27th, which is your exam 3. Your final exam, also I post on the calendar, so make sure that you have the date for the final exam. Okay, next reaction is addition of water, but this time is anti-Markovnikov of addition of water. We have heard about this hydroboration-oxidation reaction. With the hydroboration oxidation, when you only want to have one water molecule added, instead of using BH3, okay, instead of using BH3, you would use poisoned BH3. So basically, you take BH and replace two of the hydrogens with bulky alkyl group. So this is like a secondary isoamyl, which is like a bulky alkyl group that is replacing the two of the hydrogens. What's the benefit of this? Is basically poison catalyst or a poisoned reagent that would limit the number of water molecules being added to alkyne. Because two water molecules can be added, we want only one water molecule to be added. So instead of using borane, we are using poison borane. Okay? So we use poison borane for this. So we only add one. We know that when we are doing hydroboration-oxidation, the addition of the water is going to be anti-Markovnikov. That means OH will add to carbon 1. You still have enol because this carbon carries the OH group, which is ol, and the in group, which is in. So you have enol. Enol is not very stable. It's unstable. And it can do tautomerization. In this case, it's going from enol to aldehyde. Okay, but in general, you would call enol to keto because the COH changes to CO double bond. So hydrogen from the OH is going to go to the other carbon, and the single bond for carbon oxygen would change to double bond. That's the overall change that is happening here. So in a base catalyst, you remove the hydrogen first. So when you bring the base as a catalyst is going to act first. So it's going to remove the hydrogen. Pair of electron goes to oxygen. You have negative charge, and then pair of electron from the oxygen, it can be dropped in to make carbon-carbon double bond. When you make carbon-carbon double bond, then this carbon, since already has carbon-oxygen double bond. This carbon, since already has 4 bonds, when you make the CO double bond, it's going to add up to 5 bonds, and 5 is not stable for carbon. The pi bond will move over the next carbon, and it gives negative charge. So we have the anion here. After you protonate, it would change to the aldehyde or the keto form. So you have the general name is the keto form, but we know that this functional group is aldehyde functional group. So if you do oxymercuration, demercuration, or use the mercury to sulfate, the addition is Markovnikov addition. The final product is going to be methyl ketone. For hydroboration-oxidation, when you use like a poison borane, and you add water, the addition is going to be anti-Markovnikov, and the final product is going to be aldehyde. So for both hydroboration-oxidation and the oxymercuration-demercuration, you are adding water, with exception that one is Markovnikov, the other one is anti-Markovnikov. Also, remember, if enol forms, that means a carbon is going to have both functional group are OH and CC double bond, and carries both functional group. The name of the functional group is called enol, and enol is not stable. So I would prefer to go to ketone or aldehyde to be more stable. It's going to tautomerize, and it will give you aldehyde or ketone functional group. Oxidation of alkyne. So what happens in oxidation of alkyne? You're adding oxygen. When you use permanganate, if the permanganate that is added, it's at room temperature or neutral, is going to only break the pi bonds. It would only break the pi bonds, okay? And when it does break, if it breaks one pi bond, it adds 2 OH. But if it breaks 2 pi bond, would add C double bond to each one. So a double bond oxygen to each of the carbons. This is the case that you are using permanganate neutral or dilute and neutral, okay, is dilute. When you see the water here is not concentrated permanganate. So it's not very strong oxidizing agent. It's the mild oxidizing agent. It only breaks the pi bond. If one pi bond is broken, you would get OHs added. If 2 pi bonds are broken, you get the ketone, or in this case, is going to be diketone. That's under dilute condition. Now, if it's concentrated permanganate with heat applied, then it's going to also break the sigma bond. So you would end up with 2 new molecules. The next slide should have that one. Okay, so if it's hot permanganate in a basic solution and heat applied, is going to do oxidative cleavage, basically cuts through the carbon-carbon triple bond, and is going to have 3 bonds to oxygen, because you're cutting 3 bonds. So it's going to have 3 bonds to oxygen, and is in form of, when you hydrolyze it, it's going to give you 2 carboxylic acid. How many carbon each carboxylic is going to have depends on how many carbon you had on left and right side of this carbon-carbon triple bond. So remember, if you have hot permanganate in basic solution, it would cut through the triple bond. But if you use cold dilute permanganate, neutral, no acid, no base, it's going to only break the pi bonds. And with 2 pi bonds broken, would add CO double bond or double bond oxygen. If only 1 pi bond is broken, then you get OHs added to each carbon. Ozonolysis followed by hydrolysis. Remember, here we do not have the dimethyl sulfide, DMS. Okay, it's hydrolysis. So when you do ozonolysis followed by hydrolysis, is another oxidative cleavage. So it would cleave through the carbon-carbon triple bond and adds 3 bonds to oxygen. And when you add the water to proteinate, you will get the carboxylic acid formed from each side of the triple bond. Okay. Questions?